Good morning students, welcome back. This is a new lecture in the series of chapter Heat and Thermodynamics. In the last class we started heat and thermodynamics and we discussed about heat versus temperature. We discussed what is heat, what is temperature and what is the difference between heat and temperature. So let us revise once what is heat and what is temperature. Heat is a form of energy that produces in us the sensation of hotness or coldness. And what is temperature? Temperature is a measure of the degree of hotness or coldness. And if you remember, temperature used to be the deciding factor that decides the direction of flow of heat from one body to another. If there are two bodies, one body A is at higher temperature and another body B is at lower temperature, then the transfer of heat takes place from the body at higher temperature to the body at lower temperature, that is from body A to body B, right? And heat is a cause and temperature is an effect. Why? Because on heating the body, the temperature of the body increases. So heat is a cause and temperature is an effect. And then we discuss the units. The CGS unit of heat is calorie and the SI unit of heat is joule. And on the other hand, the units of temperature are degree centigrade, degree Fahrenheit and Kelvin. So these were the points of discussion, and also then we discussed about thermal expansion, of which there are three types: linear expansion, superficial expansion and cubical expansion. So what is thermal expansion? What happens is almost all the bodies, solids, liquid and gases, expand on heating, and the increase in the size of a body when it is heated, it is called as thermal expansion. And there are three types of thermal expansion: linear expansion, superficial expansion, cubical expansion. What is linear expansion? The increase in the length of a metal rod when it is heated, it is called as a linear expansion. What is superficial expansion? The increase in the surface area of a metal plate when it is heated, it is called as a superficial expansion. And what is cubical expansion? The increase in the volume of a body when it is heated, it is called as a cubical expansion. This is what we discussed in the last class. Now in this lecture we are going to take these things forward and we are going to dive into more details of what is linear expansion, superficial expansion and cubical expansion. So first let us discuss about linear expansion. So please write down the heading, the first type, linear expansion. I am going to erase this now. So now we are going to discuss about linear expansion in detail. So we have linear expansion. So now we are going to discuss about linear expansion in detail. Let's say there is a rod. There is one rod. Let's say this is one rod. And at temperature, at some temperature, let's say theta 1. Theta is equal to theta 1. I am denoting temperature here by the term theta. So there is no need to get confused. And this is what temperature? Theta 1. Okay, let me simply write it as theta 1. Okay? At temperature theta 1. So when the temperature of this rod is theta 1, the length of the rod is say L1. So this is the length of the rod L1. This is initially. Okay? Initially. And now what happens is we start increasing the temperature of this rod. We start increasing the temperature of this rod and we see that the length of the rod starts increasing, right? And finally at some temperature theta 2, and this is a final situation. This is finally, right? So initially at temperature theta 1, the length of the rod was L1, let's say, and then we start increasing the temperature of the rod, and finally we see at some temperature theta 2, the length of the rod becomes L2, where L2 will be greater than L1, right? Because theta 2 is greater than theta 1, right? I hope the things are clear till here, right? So now let's say at some intermediate temperature between theta 1 and theta 2, right? At some intermediate temperature between theta 1 and theta 2, at some intermediate temperature, at some, chalo, at some intermediate temperature, at some intermediate temperature theta, where theta is less than theta 2 and but greater than theta 1. So that temperature of the body is when increasing, we are considering one intermediate situation when the temperature is theta, where theta is less than theta 2 and but greater than theta 1. Let's say when the temperature is theta, the length of the rod is say L. Okay? The length of the rod, let's say, is L. Now, when the temperature is theta, the length of the rod is L, and suppose we slightly increase the temperature of this rod by d theta, then what will happen? There will be a small increase in the length of the rod, let's say it is dA, right? So, this is at temperature theta. And when we have increased the temperature slightly by d theta, then let's say the length of the rod increases by dA. So this is the situation at theta plus d theta, and you can see that this length is dA. So now the length of the rod becomes L plus dA, right? The original length was L at temperature theta, and when we have slightly increased the temperature by d theta so that the final temperature becomes theta plus d theta, then there is a small increase in the length of a rod which is dA, right? So this has happened. Now from the experiments we have observed that dL, now I'm proceeding here, from the experiments we have observed that dN means the increase in the length of the rod. This is the increase in the length of the rod when the temperature has been raised by d theta, right? So from the experiments we have observed that this increase in the length of the rod is directly proportional to the original length of the rod. जितनी बड़ी रॉड होगी, मान लो 1 सेंटीमीटर की रॉड है एंड आपने टेम्परेचर d थीटा इंक्रीज करा है, तो उसमें जो इंक्रीज होगा वो भी थोड़ा सा होगा, एंड अगर कोई इतनी बड़ी रॉड है एंड अगर आपने उसमें डी थीटा का टेम्परेचर चेंज करा है तो जो उसमें इंक्रीज होगा वो भी ज्यादा होगा. सो दिस इंक्रीज इन द लेंथ ऑफ द रॉड इज डायरेक्टली प्रोपोर्शनल टू द ओरिजिनल लेंथ ऑफ द रॉड, राइट? एंड ऑल्सो दिस इंक्रीज इन द लेंथ ऑफ द रॉड इज डायरेक्टली प्रोपोर्शनल टू द इंक्रीज इन टेम्परेचर. This is from experiments. So जितना ज्यादा आप टेम्परेचर इंक्रीज करोगे, जितना ज्यादा टेम्परेचर चेंज करोगे, उतना ही जो ज्यादा हमें इंक्रीज देखने को मिलेगा इन द लेंथ ऑफ द रॉड. So increase in the length of the rod is directly proportional to the original length of the rod, and also increase in the length of the rod is directly proportional to the increase in temperature of the rod, right? Now if we combine this, on combining dl is proportional to l d theta. I hope this is clear to you. Now we can remove this proportionality sign and introduce we have introduced one constant of proportionality which is called as alpha, and this alpha is called as coefficient of linear expansion. This alpha, constant of proportionality, is called as coefficient of linear expansion. Please note down till here and then we shall proceed forward, because I have to erase this because I need more space. So please copy this down and then we shall move forward. Right? I hope you have copied this. So now I am going to erase this. So I am going to erase this now. So from here we have dl is equal to alpha n d theta. I am keeping this aside. Now after this I am proceeding from here, right? Let me draw one line so that there are two partitions. First I will write here and then I will write here. So from here we have dl is equal to alpha n d theta. So can we write it as dl upon l is equal to alpha d theta, right? I have taken this l in the denominator of LHS and then we have dl upon l is equal to alpha d theta. Now we can integrate both the sides. Integrating both sides. Integrating both sides. Integrating both the sides, what do we have? Integration sign, then dl upon l, and because this alpha is constant of proportionality, coefficient of linear expansion, so it will be taken out of integration and then we will have integration of d theta. Now I need to put the limits of this integration. So if you see initially at temperature theta 1, the length of the rod was L1. So at temperature theta 1, the length of the rod is L1. And finally at temperature theta 2, the length of the rod is L2. So at temperature theta 2, finally the length of rod is L2. Right? And what is this integration of dl upon L? If you know this formula, let me write here, integration of 1 upon x dx. It is ln x. Natural log of x is the integration of this formula. Integration of dx upon x. This is of the form integration of dx upon x. So integration of dl upon L will be ln of L. ln of L, and then we will put the limits. The lower limit is L1. So I am putting here the lower limit L1 and the higher limit is L2. So I am putting this here higher limit L2. And what is this integration of d theta? It is of the form integration of dx, and integration of dx is x. So integration of d theta will be theta, and the lower limit is theta 1, the upper limit is theta 2. Right? Now we will put the limits and we will solve it further, and we have to write this alpha also here. So this is alpha, right? So it will be ln of L2 minus ln of L1, and it is equal to alpha theta 2 minus theta 1. First we put the upper limit minus, then we put the lower limit. I hope you know till here. And what is log x minus log y? There is one relation, log x minus log y. It is equal to log of x upon y. So these are some of the formulas that you need to know. Without these you won't be able to solve it. So ln of x minus ln y will be equal to ln of x upon y. So it becomes ln of L2 upon L1, right, is equal to alpha of, can you write it as delta theta, because this is the increasing temperature. If the initial temperature was theta 1 and the final temperature is theta 2, we can write it as theta 2 minus theta 1 is equal to delta theta. There is no problem in it, right? So I am writing it as delta theta. Now we have ln of L2 upon L1 is equal to alpha delta theta. Now we can take the antilog on both the sides. Taking antilog on both the sides, this ln and this natural log and antilog will cancel out. So we will have L2 upon L1 is equal to e to the power alpha delta theta. This e is called as antilog. And okay, this e is called as antilog. And what is the value of e? What is the value of e? It is 2.71. 2.71 is the value of this antilog. It is just a number like pi. The value of pi is 3.1415. So this antilog e is a number which is 2.71 something, right? So it is equal to 2.71. So from here you can write L2 is equal to L1 e की power alpha delta theta. So this is one of the important expressions. So the final length, using this formula you can calculate the final length of the rod. If L2 is the final length, L1 is the initial length, alpha is the coefficient of linear expansion, and delta theta is the rise in temperature, then using this relation you can calculate the final length of the rod. If the initial length was L1 and the coefficient of linear expansion is alpha, delta theta is the increase in temperature, then L1 e to the power alpha delta theta will give you the value of L2, which is the final length of the rod, right? So please copy till here and then we shall move forward. Please copy till here and then we shall move forward. I hope everyone has noted this down. So now I am going to erase this part so that we have more space to take our derivation forward. Now if you know one relation e to the power x, there are various series, and for that we have one series e to the power x, and it is given as 1 upon 0 factorial plus x upon 1 factorial plus x square upon 2 factorial plus x cube upon 3 factorial, and it goes on till infinity. This is one series of e to the power x that you should know. Now in this relation we have e to the power alpha delta theta. So if we use this relation, can we write it as e to the power alpha delta theta? It can be written as, I hope you know these factorial. 0 factorial is 1, 1 factorial is 1, and 2 factorial is 2, 3 factorial is 6. I hope you have studied the permutations and combinations, so you know about these factorials, right? So e to the power alpha delta theta can be written as 1 plus alpha delta theta plus alpha delta theta का square upon 2 factorial plus and so on till infinity. This goes till infinity. Now practically the value of alpha, coefficient of linear expansion, the value of alpha is practically very small, and therefore for example the value of alpha is 0.000013. This is the value of alpha, and if you do the square, then instead of these 4 zeros after decimal you will have 8 zeros. So this value, these values become very small. So we neglect these values. Right? So e to the power alpha delta theta is approximately equal to 1 plus alpha delta theta. Right? Let's say this is equation 1 and let's say this is equation 2. So if we use equation 2 in equation 1, using equation 2 in equation 1, using equation 2 in equation 1, what do we get? We get L2 is equal to L1 1 plus alpha delta theta. This is another important form of expression for linear expansion, which is L2 is equal to L1 into 1 plus alpha delta theta, where L2 is the final length of the rod, L1 is the initial length of the rod, alpha is coefficient of linear expansion, and delta theta is the increase in temperature. Right? So the value of alpha will be given to you in equations, and then using this formula you can calculate the value of final length of the rod. I hope this is clear to you. So please write it down. Please note this down. And one important thing that you need to know is the definition of coefficient of linear expansion. So during the derivation we have one term, we had dl is equal to alpha L d theta. Right? Using this equation we can define the coefficient of linear expansion. From here alpha will be equal to dl upon L d theta. Right? So if L is equal to 1 meter, if initially the length of the rod was 1 meter, so if L is equal to 1 meter and d theta is 1 degree centigrade. So we are increasing the unit, we are increasing the temperature by unit degree centigrade. By 1 degree centigrade we are increasing the temperature. Then from here alpha will be equal to dl. From here alpha is equal to dl. So we can define the coefficient of linear expansion from here. So what is coefficient of linear expansion defined as? It is defined as the increase in the length of the rod. This dl is the increase in the length of the rod. So alpha, coefficient of linear expansion, is defined as the increase in the length of the rod per unit length per unit rising temperature. So please copy this down and then write down the definition of coefficient of linear expansion. Pause the video and write it down. Right? I hope everyone has noted this down by pausing the video. So now write down the definition of coefficient of linear expansion. Definition of coefficient of linear expansion. Write down these 4 lines. dl is equal to alpha L d theta. Then therefore alpha is equal to dl upon L d theta. So if L is equal to 1 meter, d theta is equal to 1 degree centigrade, then alpha is equal to dl. And from here we can frame the definition of coefficient of linear expansion. So write down the coefficient of linear expansion is defined as the coefficient of linear expansion is defined as the coefficient of linear expansion is defined as the increase in length is defined as the increase in length of the rod is defined as the increase in length of the rod per unit 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 rise in temperature per unit rise in temperature. Right? So this is how do we define coefficient of linear expansion. I hope this is clear to everyone. Right? So it was all in this linear expansion topic, and similarly we have to do superficial expansion and cubical expansion also. So in the next video we will be covering about superficial expansion and cubical expansion. Till then, revise it thoroughly, and then we shall meet in the next video. Till then, take care and goodbye.